Hello, Yusuf. How are you? Let me turn this down for you. There we go. That's a little bit better. How you doing, my friend? How are things with you? So much to do. So, Yusuf, I wish I knew what I was doing half the time. There we go. Now we got it. Yes. Hello, 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 hello. How we doing, Yusuf? Hope you're doing good, my friend. Hope everybody's doing good today. Hope you are well this afternoon / evening. Pistache. Good afternoon to you. I hope we're doing good today. Very good. Very good. Good afternoon, Hisa. How are you? You good? I still got no words after winning the giveaway from Spencer. Yeah. Congratulations on that. Hopefully you'll be getting in the post soon. You there, Yusuf? Get the get the headphones. So let me know how they work. Hopefully they're pretty good at top quality stuff. I'm good, and you? Yeah, I'm doing really good, really good. Had a nice, fun weekend there, Hisa. Nice, got to watch the Bears game at Soldier Field. Sister took, I think I mentioned that last class, but I had a great time at the game. It was a wonderful, fun time. Now I'm back. Back yesterday. I worked all day yesterday. On my actual birthday, I worked all day. Like, yeah. And then back at it today. Doing another section with you guys. Having a grand old time. Having fun. Goofing off. And overall just enjoying the party. Enjoying the party atmosphere. What's that for a second? Ooh, got so much time to finish too, which is kind of crazy when you think about it. Oh my God, it's like week number 5 already. If you can believe it. Week 5. We're already here in week number 5. Time flies, I'm telling you. Time flies when you're doing classes all the time. Yep. Did you know? I didn't find out until last week, until my sister just kind of laid the bombshell on me, like, "Oh yeah, I'm gonna grab tickets." I'm like, "You gonna do what now?" The issue with going to an American football game, um, much like just football games in general for like the Prem, is that tickets are notoriously expensive. So, um, you want to make it, unless you have the funds, you're gonna make it a once in a you're gonna make it a once in a blue moon experience. So it's just not cheap. I don't know how much my sister paid for the seats, so they were pretty outstanding seats, to be fair. They're like right on top of the field. But the yeah, it's just how expensive the tickets are. But other sporting events are much cheaper. So, Julie, thank you. How was your weekend? My weekend was fantastic. I'm just talking about it right now. Actually, was talking about how I went to the Bears game on Sunday. Had a wonderful time. Absolutely great. Bears win. So hopefully that continues on next week. It was a crazy game though. Crazy game. How was your weekend there, Julie? Hopefully your weekend was good. Did you get a nice time? Hopefully a nice time to spend on your weekend as well. Hopefully ready for a nice, easy day. Angie, good evening to you. Good evening. How are you? What do you guys, let me go, if you like the Bears, you never believe what I was doing yesterday. What were you doing yesterday, Angie? I gotta listen to this. What you end up, what you end up doing yesterday? Actually, now I'm curious, because it's... Wait, seriously? Wow. That's amazing, really. You set up the interior home of Justin Fields. You designed his entire house. Wow. Perks of being a designer for Lazy Boy. Damn. Wow. So you got to meet him in person and talk with him and stuff? That's pretty cool. Considering Justin Fields is going to be in Chicago for a while, that's pretty awesome. I finally get to tell people now. That's cool. That's cool. Is he a pretty down to earth dude? Pretty cool dude? Seems like a great kid. Yeah, yeah. That's good. That's good. I don't know. It's just he's got that hunger to be better, but he just has that humble side on him too. So he's tall. Well, I'm sure he beat you up the stairs many times, considering that's part of his workout routine. Is literally run up and down steps. I mean, sure, I'm pretty sure if I were to try and race Justin Fields on steps, he would be like up and down like 3 flights of steps before I got up 1 flight of steps. I mean, that's just how it is. You love the entire setup? That's great. That's great. It means you did a quality job. That's really good. Good on you, Angie. That's awesome. That's awesome. That's so cool. Do you live close to the stadium, or does he live downtown, or does he live out in the burbs? I know some players like to live closer to the stadium so they can get in more practice, or they live up in Lake Forest. Biggest secret ever. If they do, then they live up in Lake Forest typically, usually to be closer to Hallis Hall. I actually, ironic story. I used to work for Lake Forest College as a student when I was a student there, so I got to go to Hallis Hall over there before they remodeled it. Now that's fine. You don't have to say. That's perfectly understandable if you have to sign an NDA. Um, no, so I went up to Hallis Hall when I was a student, and we got to work on some of their computer stuff in there. So we got to see like the Super Bowl trophy and all the case, and most of it was pretty emptied out because they were gonna switch over. But it was cool to see like a few things from previous Bears dynasties and stuff back in the day. Considering Hallis Hall is like right across from the end of campus at Lake Forest College, it's really not too hard to find. At the time, it was anyway. All right, so we got to go ahead and get started here. All right, ladies and gentlemen. All right, let's get started here. We got a few things to talk about here first and foremost. So let's do some intros and let's get moving. All right, let's do this. Okay, let's get started today. Welcome back to Tuesday. All right, hopefully you have a nice weekend. All right, so today, ladies and gentlemen, I want to give a friendly reminder here to everyone. All right, friendly reminder for everyone. Remember that the homework for chapters 1 through 3 and the test for chapters 1 through 3 is going to be due Thursday at 11:59 p.m. So if you haven't finished it up by now, you got 2 more days of which to finish by 11:59. You send me an email saying you need more time, I'm not going to answer said email. Okay? End of story. So don't bank on the fact that I'm going to tell you nothing. Be like, I need more time. I said I gave you more time. I gave you plenty of time. Okay? So You've had plenty of time to finish. Make sure you finish that stuff up. All right, 2 more days to get that done. Hopefully, most of you are finished. But if you haven't finished, well, get on that right away. If you haven't taken the test just yet, remember, do the practice test first. That'll give you a great idea, again, since it's exactly the actual test, just with different numbers, and a few more resources, give you a good idea about what to expect for the real test. Give yourself plenty of time. And also, one more thing here, please make sure to save before 11:59. Otherwise, if you save after 11:59 p.m., it will not count. Okay, so if you're trying to do things at the last minute, I guarantee you it doesn't usually go very well. But if you're going to go down that path, well, at least be aware that you don't want to put yourself in harm's way in terms of harming your grade. So, all right. So, by the way, just to ask everybody here, are there any questions about anything of that sort? Any questions about tests or homework up until this point? Again, please type no in the chat if you have no questions. Otherwise, if you do have questions, please go ahead and type those out as well. Okay. All right. So, as I mentioned here last week, we are on a good pace for the course here. We're on really good pace here. We're in week number 5. We have like a lot of time left, in all honesty. So, we are going to continue moving on here in chapter 5. What do you guys think? How does one section a day until we finish chapter 5 sound? That sound okay? Take it just a bit slower. One section a day. Yes, you guys like that? All right. Well, that sounds good. All right. Okay. C indeed. All right, let's do it, guys. Let's just take care of the one section tier today, then. If you guys really like that, hopefully we'll be we're in really good shape in terms of pace. Like, we're pretty far ahead where I want to be. So, last time we talked about the end of section 5.2. We did the general addition method. We looked at the table stuff. All right, in the textbook, we did a few examples in relation to that. Today, we're going to be doing section 5.3. So let's go to the big board here and let's see what we're talking about here today. All right. So today, ladies and gentlemen, we're going to be talking about here, independent events, okay? And what we're talking about is the multiplication rule revolving around independent events. Okay. So let's take a good look at this here, and let's see what we're talking about. All right. So, objectives, identifying independent events, and using that multiplication rule. All right. And computing at least probabilities. This is true. All right. So number one, what are independent events? Now, we kind of talked about this last time here when we talked about, say, mutually exclusive or disjoint events, or like 2 or more events, that had absolutely nothing to do with each other. So one event did not affect the other event in any which form or manner. Essentially, we're working with the same kind of premise here. So just to read this off here, says independent events are 2 or more events, A and B, or again, more than that, maybe C, D, and E, if you want more events, in which the probability of event A does not affect the probability of event B. Again, just going back to the fact that these are purely disjoint events, okay? These have nothing to do with each other, and they don't affect each other in any way possible. We can also call independent events, as mentioned here before, as disjoint events. Okay, now if they're independent events, if you remember here last time when we did the general addition rule, if they were disjoint events, like, one didn't affect the other, we would say the probability of A or B was equal to the probability of A plus the probability of B. Well, it works the same way here with the multiplication rule. We say, what is the multiplication rule for independent events? We assume that events A and B are independent events. Then the probability, in this case, though, just be a little careful about the wording here. In this case, we're not dealing with or. In this case, now, we're dealing with the word and. Okay, so remember, there is that significant difference between the wording. from what we did before and what we're doing now. So the probability of A and B is equal to the probability of A times the probability of B. So if we had 2 or more events, so I put this at the bottom here, but if you had 2 or more independent events, like n events, for example, I just labeled it as A1 to AN, you just literally just multiply every probability with each other, and that's pretty much what you got. Okay, so you have probability A1 times probability A2 times all the way up to the last possible probability. Now, I'm going to leave this up here for just a second. I'm going to put this on the split screen. Okay, but go to the paint tool here. Let's go ahead and take a look at some examples here using this rule here. All right, this is all the notes for 5.3, by the way. It's just this one page. All right, but we're going to look at some examples here, and we're going to be able to apply it and see how things work out using certain problems and this general multiplication rule. All right, let's look at that right now. I have it up here. Oh, I thought I did. Oh, I guess I don't. All right. Well, that's a problem. Sorry, I just need to grab stuff from the textbook. I thought I had a link for that, but I do not, so I'm going to have to go back and get the link for the e-text here. Make my way there again. Sorry about that, folks. Just find the page again. All right, here we go. Perfect. Okay. I'm gonna work with a couple of easy problems here, and then we'll work with a couple of tough problems as well. I think that's perfectly fine. F. All right, there. Yeah. All right, here we go. Okay, so we're gonna go ahead and start off with number 15. Okay, and then we'll look at another couple problems. We'll look at a few problems here, of course, in order to kind of drive the point home. But let's look at 15 here first, and let's go ahead and read this off here together, and we'll see exactly what we're doing here in order to find these particular probabilities. Okay, let's go ahead and get started with that. All right, so false positives. The Elisa test. Elisa is a test to determine whether the HIV antibody is present. The test is 99.5% effective, which means that the test will come back negative if the HIV antibody is not present 99.5% of the time. The probability of a test coming back positive when the antibody is not present, i.e. a false positive, is 0.005. Suppose that this test, the ELISA test, is given to 5 randomly selected people who do not have the HIV antibody. Okay, so let's look at some probabilities associated with each. All right, what is the probability that the ELISA comes back negative for all 5 people? Okay, what it comes back negative for all 5 people? Now, there's a couple ways you can approach this problem. Now, we did talk about each person here. All right, let's answer this question first. Actually, let's just step back for a second. We choose 5 people. Now, let's answer this question. You guys can tell me here. Will one person affect the other people in this group based on this random selection? So basically what I'm asking is, are these people independent? Yes or no? Are they kind of separate people from each other? Will they affect any one another, you know? Are they independent? Would you think that the sample size of 5 people would be independent? Yes or no? So yes or no, guys? You think, would the sample be independent? Yes. All right. Okay, so the answer is definitely yes. We picked these 5 people. They're truly independent in that particular manner. Now, the best way to kind of look at this here, let's talk about one of the keys here, is B. Let's put it over here. One of the big keys that I like to draw is just to draw a picture, or just make it a picture representation. So make a picture, sort of, all right, of the situation at hand. I say sort of. Let me go ahead and point out exactly what this picture means here by this key. Well, instead of like making a picture, I'm gonna, instead of like making a actual picture, because don't trust my art skills. Instead, I'm just gonna put little dashed lines here. Okay. Now I have 5 people here. Okay, 5 randomly selected people. So this is the first person here. This is the second, and I think you get the gist here. Third, fourth, and fifth. All right. We know that these are independent. Okay. So the question asks the probability that for all 5 people come back negative. That all 5 people come back negative. So probability that all 5 are negative. So let's take a good look here at each blank. If the first person is negative, what's the probability that they come back negative? Let's going to express this as a decimal, guys. So let's point that out here. I'm going to express this as a decimal. What's the probability that that the first person comes out negative for this test? What decimal would I put here in this case? .5? I don't think so. It's not a 50-50 thing, Angie. Not according to this problem here. So take a look there carefully, Angie, at the problem. All right. The one thing I want you to do, okay, not to guess here. So 1 minus 0.005, we get 0.995. So that is correct. Okay, so the probability that the test comes back negative, remember, the antibody is not present 99.5% of the time. So because it's not present 99.5% of the time, that means you'll come back with a negative test that same percentage, i.e. 0.995, or as Chioma has, 1 minus the amount of positives, which is also 0.995. And have this here. Okay, any questions about how I got that? Any questions? I want to be sure everybody's on the same page here. Any questions about why that first person there, 0.995? Because we're trying to find all of them to be negative. Okay? And 0.995 is the probability of being negative. Okay. All right. How about the second person? What's the probability that the second person is also negative? What's the probability that the second person is also negative? What's that going to be? What's the probability that the second person will also be negative? What do you guys think? Probability that so we've got the first person here at 0.995. What about the second person? Remember, you did say that they're independent people. All right? So the first person has nothing to do with the second person. The second person's its own individual person. The answer is, that's correct. The answer is also 0.995. Good. Remember, the second person is an independent than that of the first person. If the first person has nothing to do with the second person because there's two random people, then they still have the same probability as the first person. All right, how about the third person? What's that probability? Keep going down the line. What's that probability? So Giacomo's right is the same. That's correct. What about the third person? 0.995. That's right. Now you can kind of see where we're going with this, right? Each person here to get a negative result is 0.995 in terms of its probability. So now, all I want you to do, ladies and gentlemen, is just multiply this straight up as it is. So 0.995 all the way across. And so literally you're going to get 0.995 to the fifth power. Okay? If we're going to find this probability, that's how we're going to go ahead and find it. Just drawing out a simple picture and figuring out the probability for each person all the way down. And then multiplying those results together. So that seems fair. So what do we get here? Anybody got an answer here on their calculator? 0.995 to the fifth power. Or you can just multiply 0.995 times 995 times 995. So anybody got an answer for me? Again, 4 decimal places here. Is it 0.975? That exact? I don't know if that's exact or not, but I'll take you guys' word for it. 9752? Okay. Remember, 4 decimal places, guys. Not 3. I need 4. If it's 5-2, then yeah, we gotta include that fourth one there. Okay. Okay. Good. Any questions so far about that? Any questions? All right. Now you got a pretty good idea about how it kind of works here with independent events. Okay, it's not super hard. Okay, it's not super crazy. I mean, technically you can think of it as super crazy, but it's not. Okay, it's not. Now, I want to look at letter B. Okay, so let's look at letter B here. Okay, so let's take a look at this carefully here. So we did letter A, that's great. Look at letter B. Letter B says, what is the probability that the test comes back positive for at least one of the 5 people? So the probability that it's positive, do this test here, and it comes back positive for at least one of these 5 people. Okay. All right. So let's talk about this problem right here. Okay, now you remember here at the very beginning of this particular chapter, one of the things that I mentioned here is that to be on the lookout for wording here. And once again, that's just where it rears its ugly head. In this case here, we have at least one. So there's at least one positive. Now, there's a problem with this. Okay, let's talk about what that is. The problem is that, think of it this way. If I have at least one positive, well, that's a lot of different cases if you want to consider it that way, right? At least one means that there could be one person who tested positive. There could be 2 people who tested positive. 3 people could have tested positive. 4 people could have tested positive out of the 5. Or heck, even all 5 people that we randomly select could have tested positive. So in that case, we actually have 5 separate cases that we would have to go through. Finding the probability of 1 positive, finding the probability of 2 positives, 3 positives, 4 positives, and all 5 of them being positives. All right. Now we could go through each probability and add them up together and get our final result. But Let's see if you guys recognize this. Is there an easier way of doing that? What would be an easier way of doing that particular process? Instead of taking 5 separate probabilities, what do you think we could use to shorten this process down by a significant amount? What do you guys think? This is it's kind of a tough question. To be fair, it's a tough question, but it does have a reasonable answer. How can I make this problem easier so I don't have to add up like 5 different probabilities and do this calculation like I did in the first part here 5 times? That's a lot of work, and I don't want to do it. So could I make that a bit easier? What should I do here? Okay, well, how could I possibly use the answer to letter A? How could I use letter A then to help me out with letter B? good good question. I have no answer to this. Oh, okay. I will give you a hint here, Angie. Since you said that. The answer is yes, you will be using the answer to letter A, but I need the context about how you're going to use the answer to letter A. So you're on the right track with that answer, actually. But it's just a matter of how exactly are we going to incorporate it. Here's a question for you guys. Can you tell me what's the remember we did talk about something here last time, right? I think you guys may have recalled. What was the last thing we talked about in section 5.2? Anybody remember? What was that last thing that we talked about here? The very last question. Anybody remember about that? Probably have that in your notes if you've copied down the notes here so far. What was the last thing we talked about in the previous section? Maybe that could be helpful. Question mark, question mark, question mark. I know I'm not saying anything, but I'm gonna have you guys answer it for me. That's why. So, like I said, I can sit here all day. You guys will have to answer for me here. So, the rule of complements. All right. So the rule of complements. Okay, so the rule of complements says I should do the opposite. So I don't want to find the probability of positive and at least one being positive. So what's the opposite of at least one being positive? What's the probability? What's the opposite of at least one positive? Anybody tell me what is the opposite of at least one positive? Oh, careful with that, Angie. That's close though. Careful with the wording here, Angie. There's a reason why we point out at least one. You're on the right track though, Angie. No. Make it easier. Tell me, at least one positive. What's the opposite of at least one? What is included in at least one? That means 1 case, 2 cases, 3 cases, 4 cases, 5 cases, right? You guys are thinking 5 minus 1. Guys, read carefully. I want you to think of the words at least one. Guys, the wording here is going to kill you if you don't understand at least one. It will kill you in this section. I won't sugarcoat it. Not going to sugarcoat it. At least one. What's the opposite of at least one? If so, it's not form negative. So if you had this, okay, so think of it this way. Let's say how many cases we have here. We have 0, 1, 2, 3, 4, and 5 cases. All right. If I think of at least one would include these cases right here. That's correct. None are positive. That means that none are positive. So if I'm using the rule of complements, I'm doing 1 minus the probability that we have no positives. I.e., all of them are negatives. Yeah, you're thinking 5 minus 1, but you need to read, like, this is kind of like one of those things. You need to start reading between the lines here with that wording. At least one. And if it means you write out your cases here just like I have here on the right, write it out like that. All right, but I need to make this crystal clear because then you're going to keep getting the wrong answers because you can still keep applying the same thing. So, and we obviously want to be consistent with the correct interpretation here. So we have 1 minus the probability of no positives. So the probability of no positives here is what we got in the last part here, which was the 0.9752. That's the probability of all negatives. Same thing, right? So same as probability of all negatives. All right. So we get 0.0. What do we get here? 248, right? I think 2, right? All right. So we get 0.0248 is what we get here as our final answer. Oh, why did I write that twice? That looked really weird. That looks really weird. Sorry. I don't know why I wrote that 2 times. There we go. All right. Any questions about that so far? Any questions? Does everybody see where I came up with that? Any questions? Nope. All right. Well, let's try another one. I know this was a tough one. Let's try another one, guys. Let's see if you guys can, now that you have a good perspective on how to approach these problems, let's see if we can do another example. And this time, hopefully it's be just a tad bit faster. So again, first go-rounds are always tough, which is fine. So no big deal. Let's look at the next one here, number 16, okay? All right, so 16 says Christmas lights. So Christmas lights are often designed with a series circuit. That means that when one light burns out, the entire string of lights goes black. Suppose that the lights are designed so that the probability of a bulb will last 2 years is 0.995. The success or failure of a bulb is independent of the success or failure of other bulbs. All right. So let's look at letter A. All right. What is the probability that in a string of 100 lights, all 100 lights will last 2 years? All right. Oh, man, made you mad. Hey, buddy. Oh, man, thank you so much for the sub, dude. 12 months? You mean it's been a year? Seriously? 1 year? Good lord, dude. Well, if there's anything you are, it's nothing but loyal. I can't really argue with that. How you been, my man? How you been? I've been doing fantastic, my friend. Absolutely fantastic. I've been doing fantastic. It's been a, I tell you, it's been a roller coaster of a year, that's for sure. No, good to hear. Good to hear from you, man. I don't know why you keep subbing to me, man. You don't have to sub me. You're always welcome in here, regardless. You're always in here, regardless, man. You're always welcome. Your presence is always welcome at any time, my friend. Anytime. Thank you so much. It's super kind, man. Like I said, I don't deserve a sub. It's just I just hope that you have learned something. You have get stuck with me. I see how it is. I see how it is. Okay, that's fair. Oh, you can help me out. You can help everybody out. You can help. You can join the rest of us here. They say the probability that 100 lights will last 2 years. All right, so that's how we're gonna say it. So 100 out of 100 will last 2 years. Okay, so it's gonna be pretty easy. Each bulb here is independent. Okay, so each bulb here is independent. So what we're gonna have here is again, what's the probability that the bulb will last? All right, so let's look at the first bulb here. Let's look at the first bulb. What's the probability that the first bulb will last 2 years? What's that gonna be? I'm stuck with What's the probability that this bulb will last 2 years, ladies and gentlemen? All right, good. 0.995, excellent. All right, so in this case, 0.995. How about all the other bulbs as well? Are they the same probability, 0.995? Yes or no, are they the same probability? Yes, yes they are. And again, the reason why they're the same, right? We all know that the reason why they're the same is because they're each of the bulbs on the string of Christmas lights are going to be independent. Okay? So the second bulb here would be here, and again, this goes all the way down to the very last bulb, which is the 100th bulb. All right? So this is going to be 0.995. So what we're going to have here specifically, we're going to take 0.995, multiply it by itself 100 times. I'm going to have 0.995 here to the 100th power. All right. So what's that going to equal? Let's go to 4 decimal places here. What do we get here? 0.995 to the 100th power. Shouldn't be too bad to enter into a calculator. At least I hope so. 0.6057, all right? All right, so hopefully everybody got the same kind of thing. Hopefully. I'm just going to rely on you guys here, so. Participation, yes! Haha. 0.6058. Okay, now we got 2 decimals going on here. All right, now I got to figure out which one this is. Is it 5.8 or 5.7? I actually do not know. It is 5.8. Okay, it is 5.8. All right, so yeah, just be a little bit careful about that. 5.8. No, that's so. No, look, it's all good, man. We'll sweat it. Just making sure we are as accurate as possible. But no worries, we're all human. So I'm not here to punish you for your mistakes, Mike, okay? I'm only... Alright, there's no such thing as bad questions or bad answers, just a bad teacher. Alright. And somehow you got stuck with me. Alright, so... Sorry about that, guys. It was what you paid for, alright? This is what you get. This is the quality you get, okay? This is all you get, alright? Ironically, though, if all goes to plan next semester, I will be on campus next semester. So hopefully, let's cross our fingers. Let's cross our fingers. So, look, I've seen many a bad answer. Okay, look, I'm a math professor. I can't tell you how many bad answers I've seen in my lifetime. I mean, plenty of bad answers I have heard in my lifetime. Okay, that is not the worst answer I've ever heard in my life. Okay, I've heard crazy bad answers like having 47 weeks in a year, or um, I know this may seem silly, but 36, 36 plus 4 being 32. No, you're fine, Beast. You're fine, Beast. I'm just recounting a story where I saw a student write 36 plus 4 being 32. Now, the reason why that's a bad now that answer's wrong, right? And mind you, that's not the worst, craziest thing I've heard in the world. But the reason why that sticks out to me amongst many of the wrong answers I've seen in my lifetime is because this particular student had constantly complained to me because this was like back in Kansas. In Kansas, you had to take this part of their program. This one doesn't have anything to do with me, but part of the program is you had to take this like qualifying test, and this qualifying test you had to pass in order to get credit for the course. Okay, so this was done by the college, and this student had failed it like 7 times in a row, and he had to get a certain threshold, and I had to grade, appropriately here. And all he had to do, and this is 8th attempt, 36 plus 4, and he answered 32, and I had to mark it wrong, and he got below the threshold. I've never seen someone rage. I've never seen someone rage so hard in my life. Let me tell you. I felt so bad. I felt so bad because I'm like, I couldn't do it. I couldn't pass him for that particular. You had to try again, and I'm like, bro. I'm like, you almost have it. You're so close. He's like, I have to do this a 9th time. Da 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 da. Can't tell you how many swears came out of his mouth. It was plenty. Oh my goodness. 9 plus 10 is 21. Woo! Where did that come from? 20 plus 15, 25. What? The great mathematicians of our time. 9 plus 10 is 21. Clean shave, yeah. I did a little bit of a clean shave last week. So I got slightly smoother skin. My beard's starting to grow back a little bit. It grows back a little fast. Well, see, then I change ages, so that's just how it works, Beast. All right, I promise you that. All right, let's look at letter B. Beast, you could probably answer this too, possibly. What is the probability that at least one bulb will burn out in 2 years? All right, the probability of at least one will burn out. All right, can anybody tell me how we could do this particular problem? At least one burns out. Don't worry about it. If you haven't done probability yet, that's not a problem. We're going to be doing some more examples here, so you'll get to learn a little bit about how things work, at least in this regard, for independent events. Probability of at least one bulb burning out. How can we do that here? At least one out of the 100 bulbs burns out. All right, that is correct, Angie. Very good. So we're going to do 1 minus the probability that all 100 last 2 years. Again, no bulbs burn out is the opposite of at least one burns out. Let's talk about logic here. Yeah. So 1 minus 0.6058, and we will get here, what do we get here? 0.3942? Yeah, 3942. Yeah, 3942, spot on. I don't need a calculator for that. That one's so easy. All right. All So that's how you can figure it out here. Again, what does logic state? Logic states that if we have at least one burns out, the opposite of at least one burns out is that none of them burn out. So that is the opposite there in that respect. All right. Any questions about that problem there? Any questions before we move forward with another? Any questions before we move on? All right. No. All right. Let's do another. All right. Let's do another. Okay. Let's look at. Let's see which one I want to do. Yeah. Let's try that one, and then we'll see how things go there. All right. Let's do that. Go ahead. All right. Let's do number 20. All right. So number 20 here you see on the left-hand side of the screen. Okay. So quality control. Suppose that a company selects 2 people who work independently inspecting 2x4 timbers. Their job is to identify low-quality timbers. Alright, suppose that the probability that an inspector does not identify a low-quality timber is 0.20 or 20%. What is the probability that both inspectors do not identify a low-quality timber? Alright. So, in this case here, we have 2 separate independent people that are just doing some QA stuff. Alright, seems fair. So we're going to have the first inspector and the second inspector, just like so. Alright, so this is our first, and this is our second. Okay. So what's the probability that, what should I put for the first person here? What probability should I have here for the first person? In which case, both inspectors do not identify a low-quality timber piece. What am I going to have here? 0.20 is correct. That is correct. Yes. How about the second person there? How about the second person there? Also 0.20, correct. So we're just going to multiply these from each other. 0.20 times 0.20. What do we get here? 0.80. For the next person there, Chiyama? We want to say both inspectors do not identify a low-quality timber. So again, the first inspector, looks through the timber, and then it's 0.20, so he doesn't identify it. The second person goes through the same, he gets passed it off from the first guy, and then that guy looks through, and he doesn't see any low-quality timbers, so that's going to be 0.20. Yeah, that's why it's not 0.80. It's because he's like, first guy looks, he's like, okay, I don't see any low-quality stuff. Now I'm going to pass it off to the second guy, let him take a look, and then have him independently process and say, okay, is it yeah, is it nah? Then he's like, nah, there's nothing wrong with this lot. All right, so 0.20 times 0.20, what's that going to be, guys? What we got here? 0.20 times 0.20 is 0.04. Good. So this is why a lot of times having a lot of nice quality inspectors here, QA people, will be very good for your business. Save a lot of money. Save a lot of time. There you go. All right. Let's look at letter B. Letter B here. All right. Letter B says, how many inspectors should be hired to keep the probability of not identifying low-quality timber below 1%? Okay. Now, this problem here may seem a little bit tough, but I'm going to guide you through this particular part here. It does ask how many inspectors should we have, all right? Meaning to say, if we have one lot of timber and none of them identify any low quality of timber, see, then you work in QA, man. You do a QA is like the most important part of the business, 100%. That's where you basically make your money. Make your money in quality assurance. You can work on the part, and that's good. That's what the guys are there for. But quality assurance is like saying that puts the reputation of the part and the company, and they ship it away, and then hopefully part or product or whatever you want to call it. And definitely, probably, in my opinion, probably the most important department. You give up bad products, well then guess what's going to happen? The company's going to go under. Good quality assurance is best quality assurance. So if your company has, if anybody has a if any company hires one in the future, that's going to be a damn good quality assurance department. I guarantee you that. All right, right one. I know you take pride in your job. So, all right. Let's take a good look here. For 1%, this identifying of L's, yeah, well, I approve. Well, you got to identify low quality timber. So all you got to do here specifically is just figure out until you get below this 1% threshold. Remember that 1% here specifically is equal to 0.01. So you're just going to basically do a little trial and error because you're basically going to say you have 0.2 all the way down. So maybe you try it with 3 inspectors. You do 0.2 to the third power. And you say, is this going to be below 0.1? That's basically how you're going to view it here. So I try it out, and I would say I get 0.008 if I try out 0.3 inspectors here. So the answer here would be, in this case, 3. At minimum, I should have 3 inspectors because that gets me, that 0.008 is slightly below the 0.01 threshold that I'm looking for here. So that way I'm on task. I'm making sure that I'm not identifying low quality timber below that 1% threshold. So the answer to this one here is 3 inspectors. Again, if 3 wasn't the case, you would just go to the 4th power, you'd go to the 5th power, you go to the 6th power, and you would keep going until you get below that threshold. In this case, we only needed to try 3 of them, which is fine. So that's how we can go ahead and grab that. All right. Any questions about that one there? Any question? All right. Let's go ahead and take a look at another problem here. All right. So this one is for baseball. Okay. Let's look at 24. Okay. Okay, so 24 here. Players in sports are said to have hot streaks and cold streaks. For example, a batter in baseball might be considered to be in a slump or cold streak if he has made 10 outs in 10 consecutive at-bats. Suppose that a hitter successfully reaches base 30% of the time he comes to the plate. Okay, so let's take a look at letter A really quick. So find and interpret the probability that the hitter makes 10 outs in 10 consecutive at-bats. All right, assuming that at-bats are independent events, and they are. Hint, the hitter makes an out 70% of the time, okay? So here we have, again, safe. A safe one here would be, again, 0.30, would represent 30%. And an out here would be 70% of the time here. So let's go ahead and see how this works. Again, we're going to be out 10 outs in a row. So we make 10 consecutive at-bats and we make 10 consecutive outs. So we take an out and then we just do that all the way down. That's the first out, and then we make the 10th out here. So Letter A isn't too hard to do. I have 0.7 here, 0.7 here, 0.7 all the way down. Okay. So we're going to have 0.7 to the 10th power, just like so. Okay, so first and foremost here, can anybody tell me what is 0.7 to the 10th power? What is 0.7 to the 10th power? Let's at least have 4 decimal places for that. Point 0.7 to the 10th power. Anybody got an answer for me here? 0.0282, okay? All right. Now that you guys have that for letter A, okay? So you guys, that is correct. Now that you have that for letter A, we're going to immediately answer letter B from this particular question. All right, letter B says, are cold streaks unusual? So is this unusual to get 10 consecutive outs? Is it unusual to get 10 consecutive outs? Well, this is the probability of 10 outs in a row. All right. You say, Giamma says yes. Is it unusual to get 10 outs in a row? Giamma says yes. Let's see what other people have to say. Okay. The answer is yes. Okay. So you guys say yes, but why? Why is it yes? Why is it unusual to make 10 consecutive outs? Why is it unusual? Less than 0.5 or 0.05? Which one is it? 0.5 is 50%, 0.05 is 5%. Careful about that. Ah, there we go. All right, good. So that is correct. We had the definition here for unusual. Remember that the definition here of unusual, we haven't really used it too much here, but like I said, you do see some questions related to unusual here. In this case, this is less than 0.05, okay, i.e. 5%. All right, we have a probability here of 0.0282. So the answer is yes. Getting 10 consecutive outs in a row is very unusual underneath these circumstances. Okay. All right, let's look at letter C. I'll have you guys try letter C. So here we're trying to find the probability that the hitter makes 5 consecutive outs and then reaches base safely. So 5 outs and 1 safe hit. Let's have you guys take a minute. Go ahead and figure out how you can find the probability of 5 outs, and then after those 5 outs, you make 1 safe hit after that. Give it a... Again, once you have your answer there, go ahead and post that in the chat, guys. Remember to post your answer there once you have it. 5 consecutive outs and 1 safe hit. All right, she almost says 0.0504. All right, let's see what other people have to say. Big Chimpin got the same result. About 0.0504. All right. If anybody else came up with those anything same or this or different. All right. All right. Let's give it another 15 seconds or so. Maybe some people came up with the same result here. All right. Okay, let's go ahead and take a look here. Again, we have 5 outs and 1 safe hit. So again, just putting this in order here. Let's say each of these first red slashes here happen to be our 5 outs. And then finally we have our 1 safe hit here in purple. Okay, so we just take a look at the odds here of getting an out, which is 70% from our problem here. So that'll be our first 5 outs. And then our odds of getting a safe hit here is going to be 30%. So we're going to have 0.7 to the 5th power times 0.03. Not 0.03, 0.3. All right. So again, I'm going to plug that into the calculator there. And so here we get 0.0504 is the correct answer here. So in reality, this is just a touch. This would not be, actually, ironically, a part of this problem. This is not unusual because it's a touch above 5%. So, again, not unusual in this case. Very low likelihood, but not unusual. All right. Any questions about section 5.3? Any questions? Hopefully that makes a whole lot more sense compared to the first example. So first example is always the toughest one, but once you start seeing, through, using at least and things like that, it becomes significantly easier to do as we do some more examples. Any questions? Like everybody's. Boop. I don't know if we're on a delay or not. I know we're on a slight delay, so. Nope. All right. Okay. You have a question? Go ahead, Shioma. What's your question, Shioma? Ask away, my friend. I hope everybody's been doing the The empirical rule, if you're talking about, so did you, so really quick here, if you're doing empirical rule problems, did you do you have the drawing of the chart there, for using the empirical rule? Again, the empirical rule, another name for the empirical rule is the 68, 95, 99.7 rule that we talked about before. So if we were to look at this here, open up a new guy. So again, that was using the normal distribution here. That looks pretty terrible. Let's try again. That was using this dude right here. Yeah, the bell shape. So again, you get cut in half right here at the mean. Then you could go plus standard deviations over here. You go minus standard deviations over here, whatever they give you. And then if you want to understand this, again, the way the empirical rule always works out, it always works out the same way. So you have, say, minus 1 standard deviation. This is plus 1 standard deviation. You could go, I don't know why I put this as dotted lines. It should be solid lines. My bad. I think it's just out of habit. You can put this in blue. Again, this is plus 2 standard deviations. This is minus 2 standard deviations. Like this picture that I'm going to show you here is going to be pretty much, is no matter what, underneath the empirical rule is always the same exact picture. Like it doesn't change, right? It doesn't change in terms of the numbers or anything like that. These numbers that I'm going to put here in terms of percentages are exactly the same regardless. All right, so the only things that change, of course, are what these represent. What does 1 plus 1 standard deviation represent? What does minus 1 standard deviation represent? What's the mean and standard deviation of whatever they give you here? So let's say, again, this is, what is it, 13.5. You always get 2.35 here. You always get 0.15 out here. All right. So this is the generic shape of the empirical rule. So basically what this is asking you essentially here at the end of the day is, let's say you have a mean here. Let's say we're given specifically here a mean of, I don't know, we'll go with something simple. We'll go with the mean of 16 and a standard deviation of 3. Okay. So the one thing that I would suggest you do is, if you're going to make this easy on yourself, Chioma, for questions that use the empirical rule, when you have this picture here, just right below where it says mean, plus 1, plus 2, plus 3, or minus 1, minus 2, minus 3, go ahead and put those values in based on whatever mean and standard deviation they happen to give you in that problem. So if they give you like a mean, hey, the mean of this is going to be 16 and the standard deviation is 3. Even if with complicated decimals, you can still do the same thing. Because all you need to do is you start off right here in the middle, like in the mean here is 16. So if you add 1 standard deviation here, for example, well then you're just adding 3 because that's what the standard deviation is equal to, given to us, just by random happenstance. So again, I would have 16 plus 3, which would be 19. And then I had 19 plus 3, 22, and then 25 after that. And now I just go backwards here. If I'm subtracting, I'm taking 16 minus 3, that's 13. Here I get 10, and here I get 7. So if they ask you on a question here, they're like, oh, well, what is the percentage of data items that are bigger than, what's the percentage of data items that are, let's say, let me go with this. Let's say percentage of data items bigger than, percentage items, let's say bigger than 19. Okay. So let's say you go with just some random thing like that. Well, then all you have to do is just you look at 19. 19 is written right below this line here. And you add up all the percentages to the right of 19, which is 13.5, 2.35, and 0.15. And so this is going to be, in this case, this will be 16. So that's basically how you can use the empirical rule in those particular problems. Now, let me ask this question, Shioma, and let me see if I'm right about this. You probably also are wondering what happens in the part after that, because I think some people had questions about the homework in relation to that particular section and in chapter 3. And that had stuff to do with what is the actual percentage of data items that were at, that was like above or below a certain particular like range of data items. So like between, like, I think the example in the problem is like 0.7 and like 0.9, something like that. So, and then you had to actually say, well, how many are there between those two? Did you have issues with that as well? I don't know if you had issues with the next part that comes after that. Let me know about that. Otherwise, if it's just empirical rule, well, this is the topic entirely in terms of this. This is basically the entirety of the topic. So if you're talking about it, have this picture available to you, and then you just go ahead and, again, put in the values that would represent the mean, go left and right by the standard deviations, and again, just use the percentages that you have in the picture, and you can find the respective percentages. Thought I knew what I was doing. Yeah, so do I. That's not always true. To tell you what, Shioma, meet me on Discord. We could take a look at a problem or so, okay? Let's work on it. Let's work on a problem together. So we can meet on Discord though, okay? I'll put my Discord link on it. Here you go. That's my that's to my Discord channel thing. All right. Any more questions? Any more questions? We'll talk a little bit in just a second, Shioma, after I'm done with the stream. Any more questions, anyone? Before we head out here. No? All right. Well, that will take care of it for today, everybody. I want to thank everybody for coming on out here to the stream today. Thank you so much, everyone. You guys are absolutely fantastic. All right, absolutely fantastic. You guys are great. Love you guys. You guys are wonderful. Again, we'll be focusing on another section here for next time. All right, we'll be doing section 5.4. Just keep moving forward here. We'll be talking about conditional probability here. All right, so conditional probability is next on the agenda for Thursday. All right, in the meantime, though, Chioma, I will see you in a minute or two. Again, please click that link, Chioma, and you will get invited to the Discord server. It's free. Okay, you have to pay nothing, and it'll take you directly there. All right. Okay. All right, everybody. Thank you so much, and I will see you all here on Thursday. Chioma, I'll see you in a minute. All right, have a great one, everyone. And remember, stay safe, stay healthy, and most importantly, stay sane. Have a great day, everybody. Evening, afternoon, whatever the case may be. We'll see you in a couple days, everybody. Take care of yourselves. Have a great one, everyone. All right, see you later. All right, bye. Bye, everybody.